All right, welcome to the remainder section 15.6. Today we're just gonna do a few examples. Okay, so here comes the first example. Find volume of the solid bounded by surfaces y equal z square, y equal x square, y equal 1. If we project it on the xy plane, then we don't have to deal with the intersection. Okay, so you push this whole thing onto the xy plane, right? Luckily, on the xy plane, we have a y equal x squared and y equal 1. So y equal x squared, y equal 1. Okay, so the intersection right here is your region D. It is better to do which one? dA is dy dx or dx dy? Well, if you do dx dy, then you're gonna have to deal with the square root. I wouldn't recommend it. It's gonna be dy dx. It's better to do dy dx because y gonna be between the two curves and then x just between the two numbers. One of them is gonna be -1, the other one is gonna be 1. So it is better to do the dy dx. Y go from x squared to 1. Okay, so we have the dA. The volume is the 1, 2, 3. Okay, 1 dz dy dx. We know y go from x squared to 1, and then x go from -1 to 1. What about the z? Z is the height. So z go from okay. Yep, it is the setup, and I'm just gonna do one more step so that you see that you can set this thing up as a double integral, and it is just well, the derivative of 1 is z, right? And then z is equal root y, so root y minus root y is gonna be root y minus root y. dy dx. Work it out, and the answer is going to be a/3. Yay! Computer math of a solid having density rho x y z equal k. Well, and it's bounded by the surfaces x equal y square, x equals z, z equal to 0, x equal 1. Okay. Well, first thing to do is, man, you got to somehow sketch out the solid so that you guys can see exactly what it looked like. I'm going to sketch out the parabolic cylinder first here, and then you're going to get cut off by the plane. So here comes the parabolic cylinder. X equal y squared, so it's going to have to go this way. Okay. Yeah. And there's going to be a this is the x equal y squared, huh? And then they're gonna get cut by the plane. The plane is the, well, x equals z, so that plane is gonna cut it. This plane right here, see. Okay, so z equal to 0 is the xy plane. Is this the bottom part right here? Everybody knows z equal to 0 is down there. X equal 1. There should be a plane x equal 1. Well, right here it's gonna be 1. And okay, that's what it looked like. It's best to project it onto which plane? X, Y, Y, Z, X, Z, which one? So when you project it onto the X, Y plane, well, we have a X equal Y square and X equal 1. Ta-da! Oh my God, that just cut it. Yeah. Region D. DA here is, well, because look at it, it's extra. It is better to do it at dx dy. So x is going to be between two function and or between two curve, and then y is going to be between two number. Luckily, the intersection here is the 1 and -1. So -1 to 1, and then x go between the y square to 1. Yeah. Okay. Here we compute the mass, right? It has a density, so mass is gonna be 1, 2, 3. Density is k. Well, because d is dx dy, so in here it's going to be dz dx dy. Okay, we know x go from y square to 1, y go from -1 to 1. Where does z go from? Z, anybody? 0 to x. Yep, but we can work it out because it is not that bad. So I'm going to move the k outside, and this is just k, right? No, it's just x in here, dx dy. Well, half of x square y square 1 dy. Where half of 1 square is going to be half. Actually, I'm going to move the half outside here, make my life easy here. Okay, x square, and you're going to square this sucker up, so it's y to the 4th. Okay. Well, this is integration from -1 to 1. Is this function even? Yes or no? K times 2, 0 to 1, half of 1 minus y to the 4 dy. And what do we have? We have a k. So y minus y 5/5, 0 to 1. So in the end, what do we have here? We have a k 1 minus 1/5, 4/5k. Yeah. Computer math. Of a solid having density rho x, y, z equal root of x square plus z square, and is bounded by the surfaces y equal x square plus z square, y equal 4. Okay, shouldn't be too bad. You guys can do this. A paraboloid, y equal x square and y equal to z square, so y equal x square. And then the other one is y equal to z square, so a little bit bigger here. Get a nice parabola here. If not, I'm just gonna fix this thing up. Yeah, try the other one out later. This the y equal x square, and the other one is the y equal to z square, right? What we get is a paraboloid, and then this one is the y equal 4. Projection of E onto the xz, project E solid onto xz plane. I gotta get this thing. And of course, because this is the solid, right? This there. It's best to convert everything into a polar coordinate. But then we're gonna do the conversion in a bit, right? The first thing is that I'm gonna show you the full setup here. Here comes the mask. Actually, let's just do D as region D. Right. Well, from here you can do dA is the dz dx there, because I already have the x. So z is between negative root of 4 minus x square, root of 4 minus x square, then x is between negative 2 and 2, right? And then we can see the y. So y go from the paraboloid to the plane. Here come the mass. In here is the density, so root x square plus z square dy dz dx. Well, from the region D, we see that this is the negative root 4 minus x square, root 4 minus x square, negative 2 to 2, and y go from, you can see, from the paraboloid. So that is the x square plus z square to 4. That's a polar coordinate here. Using polar coordinate, the angle is from 0 to 2 pi. The radius is from 0 to 2. Right? So, but then for the polar coordinate here, you still have a x square plus z square 4 root x square plus z square dy dz. Instead of dz dx, it's going to be r d theta. you don't want to do the polar coordinate too early. Just polar coordinate is for double integral. So just save this thing here. You can rewrite this one as the d. Let's see. And then this dA. Work out this thing first before you turn everything into a polar coordinate. So it's going to be a 4 minus x squared minus 4 minus x squared plus z squared root of x squared plus z squared dA. And now you're going to turn everything into polar coordinate. Well, when you do this, it makes much more sense. So 0 to 2 pi, 0 to 2, 4 minus r square, square root of r square, r d theta. And you guys can work it out. Yeah. Work it out. Then you're going to end up with 128 pi over 5. Remember, polar coordinate is only for double integral, right? So that means you got to do the inner integral first before you can use the polar coordinate.
Okay.